Let's continue with the temperatures in cutting process. Why temperature actually increases in cutting? We have several reasons. First of all, we are trying to deform the workpiece plastically, and we need to move it. We need to dissipate energy, and once we dissipate energy, then that will be converted into heat, and this heat will increase, raise the temperature of the cutting zone, and also the workpiece and the tool. And obviously, this temperature rise has some adverse effects on the tool and the workpiece. What are these? First of all, this high temperature decreases the strength, hardness, stiffness, and wear resistance of the cutting tool. So in summary, the life of your cutting tool will be decreased if you have higher temperatures around, if the temperature of the cutting tool is increased. On the other hand, if you again have high temperatures, then this will modify the structure integrity of the machine surface, and the quality of the resulting part will be low compared to the case where you have less temperatures around. Another case is that if you have excess temperature, once again, you may have thermal damages, and you may modify the metallurgical properties of the workpiece, and again, it will affect the overall quality of the resulting products. And here you see the main sources of the heat during the machining. First of all, the first one is about the shearing in the primary shear zone. And then we have some friction while our chip is moving over the rake face. And lastly, we have again friction between the machine surface and the flank face of the tool. If you have such little angles, if the clearance angle is very low, then it's most probable that you have more friction and the heat generated will be more, and this will increase the temperature of the workpiece and also the temperature of the cutting tool. And here you see a typical temperature distribution of a cutting tool and workpiece and chip. You see that we have high temperatures usually at the tip of the tool, and also in this secondary shear zone. This is about 700, and we have about 600 around the tip of the tool. So we should be careful about it and try to decrease the temperature of the cutting tool. And on the other hand, we have less temperature on the, as you see, workpiece. It's around 100, since the workpiece is a bit huge compared to the cutting tool. That's why its temperature cannot be increased to 500, 400. The capacity, the thermal capacity for workpiece is very high. And let's jump to tool life. This is somehow related to the temperatures of the cutting tool, since if the temperature is higher, then that means we will have many deflections, some cracks may occur, some wear may occur, and these will decrease the life of the tool. And that's why now we are going to discuss the tool life after the discussion of the temperatures and cutting operation. And in the cutting operation, our tools are usually subjected to high localized stresses especially at the tip of the tool. We have high stresses there. We have high temperatures due to the friction along the rake face. And we also have the chip sliding over actually at very high speeds over the rake face. And we furthermore have, once again, sliding on the flank face. This again results in an increase in the temperature, and also they result in some wear on the cutting tool. And we can see now some typical wears on the tool. And the most popular one is actually the flank wear. And as the name implies, this happens on the flank face of the cutting tool. These are some pictures, and this is another schematic showing the flank wear. We have an average flank wear. We will be using these while defining the cutting tool life. And in addition to flank wear, we may have some craters. This is a type of a crater wear. We will talk about them in a moment. And the depth of craters are important. and they usually happen, these craters usually happen on the rake face. You may rarely have on the flank face, but the craters are mostly related with the rake face of the cutting tool. But the flank wear, as the name implies, it's always happening on the flank face of the cutting tool. And furthermore, you can see wiggled up edges here. We discussed them while we were talking about the types of chips generated during the machining process. They also affect the life of the tool. If you have a huge amount of wiggled up edges, then you may even break the tool, then that means the tool actually reached its end of life and it cannot be used anymore. Now let's focus on flank wear, and then we will be discussing the other types of wear. Flank wear is quite important since around 1890s, Taylor come up with a relationship between the amount of flank wear and the life of the tool. And this flank wear actually happens due to the rubbing of your tool on the machine surface, since on the flank face of the cutting tool is moving in this direction, let's say, and it's always rubbing with the machine surface. Another reason behind flank wear is the high temperatures. Again, this is one of the biggest issues in tool wear, and due to these reasons, actually, we have flank wear, and if the amount of flank wear is above certain value, then we can say that the tool actually reaches end of life, and we need to replace the tool or resharpen it and try to give a new life to the tool and use it once again. The equation of Taylor is that we have a relationship between the cutting speed and the tool life, and this multiplication along with this power exponent n is equal to a constant. As you see, this is v times t to the power of n is equal to c, and here c is a constant, n is a constant again, and they depend on the type of workpiece you are working on, type of cutting tool material, other conditions. They all affect the value of n and c. And how we determine these actually, let's say we set a condition. We say that, let me talk about on this picture. We say that if the amount of flank wear is, let's say, 5 millimeter, we say that the tool actually reaches end of life. At that point, we should determine the time. The tool life is determined in such a way you need to do several measurements after some time. Let's say after each day, you do measure the actually flank wear. If it's above, let's say 5 millimeter, then you say that the life of this cutting tool is 10 days at the cutting speed of, let's say, 100 millimeters per revolution. And we do it by actually some experiments. We perform such experiments. At least two experiments are required. Once you have 2 experiments, then you can, let me show you on a logarithmic plot. This is a logarithmic plot. As you see, on the x-axis, we have cutting speed. On the y, we have the tool life. So what we do, we perform at least 2 experiments and assume that one of the experiments is here, which means that at this value, this is our cutting speed. If you perform all the machining operations at this cutting speed, you will realize that the life of your tool is, let's say, about 3 minutes. And we note this one, put this point here, and then perform another experiment. Let's say we perform it at a cutting speed of 300 meters per minute. And again, note the tool life, which is about 15. And then what we do, we simply draw a line in between these 2 points. And this is actually our tool life curve. As you have seen, we have obtained this one through experimental data. And once you have it, then you can easily determine N and C values. How we determine it? C is very simple. C is actually the cutting speed at tool life is equal to 1 minute. and 1 minute is here. So if you make it longer, to the intersection of our tool life curve with the x-axis will give us the C value. So this is already determined. What about n? N is, since you have the curve, you can easily determine it. It's the negative reciprocal of the slope of these curves. And with the help of, again, this line, you obtain C and N. Then you are done. You don't need to do more experiments. You can easily determine, let's say, if you want to determine your cutting speed at this, let's say, 250 meters per minute, then what do you do? Since you already determined C and N, and you know the cutting speed, then you can determine the tool life using this simple equation. That is Taylor's tool life equation. And as we discussed in this equation, the most important factor is the flank wear, but there are also different versions in which you can use a different criterion. It might be machining power or a different type of wear. But since the most important one is the flank wear, that's why we are always considering flank wear instead of other types of wear. And in this equation, actually, N is mostly depending on the tool material, not purely, but it mostly affected by the cutting tool material. You can see some typical N values for different cutting tool materials. For simpler materials, this N value is low, as you see, but for high quality cutting tool materials like coated carbides or ceramics, we have higher N values. And on the other hand, for the C depends mostly on the workpiece material, but it's not purely depending on that. The most important factor in C is the workpiece material, and as I mentioned, it's actually the cutting speed for 1 minute of tool life. Now we can write this equation in a different form, the same equation. With the help of this form, we can easily see the importance of N, and for the constant value of C, for a constant value of, let's say, cutting speed at 1 minute of tool life, once the value of our N is low, if you use simpler cutting tool materials, then you will get less tool life. So for same cutting speeds, for same workpiece, if your N value is lower, then that means you will not be able to use that cutting tool for a longer time. The life of your tool will be lower. And in addition to cutting speed, we can also have other factors like depth of cut, feed in this equation. We can do the same approach. We can apply, we can perform similar experiments and try to determine the exponents of these variables, depth of cut and feed. But you will see that they're not as important as the cutting speed. So that's why we prefer to keep it as simple as possible. This is our simple equation. Instead of adding a depth of cut, feed in this equation, it's enough to have just cutting speed. Otherwise, it will be complicated and you will need to spend more time on the experiments. Here are different examples. We have, as you see, different materials, and their effect can easily be seen here. If you have, let's say, annealed material, its hardness is higher. So you see that the cutting tool actually, the life of the tool decreases again once you increase the cutting speed. But if it's an as casted material, you see that we cannot operate them at higher speeds. It's not possible. But if you are using an annealed material, then that means we can use it at even this high speeds. But for materials like as-cast materials having hardnesses around more than 250, you cannot use them at higher speeds. These are the things we discussed. please have a look at this example. It's very informative. Make sure that you understand what is going on here. Let me talk about briefly on optimum cutting speed. So we are trying to actually set an optimum cutting speed, since we don't want to perform the machining at very low speeds. If you do it at very low speeds, the life of the cutting tool will be higher, but the problem is that you will need to wait for machining a lot. So we are trying to find an optimum cutting speed so that the life of the cutting tool is fine, and also the production productivity is acceptable. That's why actually we are making use of such equations to determine the optimum cutting speed. Now, after flank wear, let's talk about different types of wears. The second important one is crater wear. Again, as the name implies, on this wear we have craters, and these craters are mostly formed on the rake face. It's an example. The second one is crater wear. You can see this crater wear on different cutting tool materials, on carbides here, and again on ceramic we have it, and on this again ceramic cutting tool, but this time in addition to the crater wear we have other types of wears. So why do we have crater wears? Reasons are somehow similar to the flank wear. If you have high temperature again and high let's say rubbing due to the chips generated, you may have such craters generated. Another thing about the crater, another reason is the chemical affinity. This chemical, let's say, inertness highly affects the formation of the craters. If there is some relation, chemical relation between the cutting tool material and the workpiece material, then it's probable that during this cutting operation, some material will be removed from the rake face. But if they are chemically inert, then it's not possible to have craters on the rake face. Furthermore, we have some other types of wears, but they are less important compared to flank wear and crater wear. What are these? The first one is nose wear. I think we had some examples of these in the earlier pages. They should be somewhere above. Here you can see a nose wear. At the beginning of the process, we have a kind of a pointer, sharp edges, but after some machining process, this part is actually removed and we call it as a nose wear. We've talked about other ones. Edge rounding, as the name implies, the cutting edge becomes rounded, and furthermore, due to the plastic deformations, due to the high temperatures, your cutting tool may lose its shape. So this is a general deformation at a specific deformation on a specific point. It's about the overall geometry of the cutting tool. And lastly, you may have some notches, grooves due to the impact forces or due to special, let's say, contact with the chips. These are all we can say about cutting types of wears. And as I said, the most important ones are flank wear, and the second important one is crater wear. Now that we've talked about surface finish and integrity, they are a bit different from each other. Let's talk about surface finish. It's actually describing the geometrical features of your surface, like the surface roughness values, the quality of it, but it has nothing to do with the metallurgical behavior of the workpiece. But on the other hand, the surface integrity is something different. It's highly related with the mechanical properties like fatigue life, corrosion resistance, and it's mostly affected by the machining processes and the quality of the surface. But the surface finish and the surface integrity are not the same thing. Let we talk about the last topic of this chapter is the machinability. And when you say a workpiece is machinable, then that means it will be easier to machine that product with the available equipment. And we can define it in terms of 4 factors. What are they? The first one is surface finish and surface integrity of the machine part. If the workpiece is machinable, then we can say that the resulting surface will have higher quality, surface roughness will be low, and the surface integrity will be much better if the workpiece is an machinable one. What about the tool life? We can say that if the tool life is longer, then that means this specific workpiece material is highly machinable with the selected cutting tool. What about force and power requirements? If you are consuming less power, or if the cutting forces are less, then we can say that that specific cutting tool workpiece material is machinable. And lastly, it's about the level of difficulty in chip control after it's generated. So if you can control the chips, then we can say that that workpiece material is, the machinability of the material is very high. So these are the 4 factors which are actually defining the overall machinability of a specific material. And I think we should have a last topic. This is about terminal assist machining. As the name implies, in order to make machining simpler, in order to use less cutting forces, less energy during the machining process, what we do, sometimes we increase the temperature of the workpieces. And what is this temperature? We try to increase the temperature of the workpiece to the above of their homologous temperature, and their homologous temperature is equal to the 0.5 times the melting point temperature of this workpiece material. If the temperature is above that value, then we can say that the cutting forces will be less, and we can generate chips in an easier way compared to the cold machining. Please make sure that you have a look at these questions here, review questions and other qualitative problems. And see you in online sessions.